In this section, I want to talk about how you go from LAN technology that just covers one house up to the worldwide internet, where any computer can talk to any other computer. So the way this works is you can think of the worldwide internet as sort of a phone system for computers where they're scattered all over, and every computer has essentially an address, and any computer is able to attempt to make sort of a data call to any other computer. So that's where I want to get. How does that work? So the worldwide internet is based actually on some government-funded research in the 70s from the United States, creating some standards called TCP/IP. And TCP/IP are free and open standards. They've obviously been enormously successful. They're not proprietary or specific to any vendor. They're just anybody's free to implement these. And one of the lessons of the internet is that for sort of basic infrastructure like that you want a lot of different organizations to use and feel they can build on, having it be an open standard is really the way to go. All right, so let me talk about how this works. So the first thing to know about the internet is that every computer connected to the internet has an IP address. And so what this looks like, so for example, here's my picture of the internet. So for example, the computer in my office, its IP address is 171.64.64.166. That identifies my computer. Over 30 miles from there, there's another machine I maintain, codingbat.com, and it has the IP address 173.255.219.70, and so on. So these are IPv4 addresses, which are very widely used on the internet today. There is a revision called v6 that's kind of in the wings, but hasn't really taken off yet. So the thing to know about these IP addresses is that it's actually 4 bytes. Those are 4 numbers, each between 0 and 255. So another thing to know is that the left part of the address is roughly indicates the neighborhood. So for example, the Stanford campus is generally 171.64. something. And in my building, it's 171.64.64. something. So for example, the office next to mine, a computer in there might have an address 171.64.64, maybe .164. So locally, just the right number changes, and the left part indicates more sort of on the internet where this thing is. So it's like phone numbers in the way that you have the country code and the area code. You can't just pick them out of the air. They sort of indicate where that number is. There's a somewhat famous blooper in the movie The Net, where Sandra Bullock types in an IP address 2375.345.200. Peals of laughter fill the theater because 345 is too big to fit in a byte. So that's not completely takes me out of the movie. Alrighty, so I'm going to zoom in on this picture, explain how more parts of this work. One thing I should just mention is most of my discussion today will talk about IP addresses. That is how it works under the hood. But we've got these familiar names like nick2.stanford.edu or codingbat.com. Those are what are called domain names. And domain names form effectively kind of a shorthand for IP addresses, but they use just regular words and dots. So it's easy for a person to remember or to type. The way it works is there's essentially a worldwide directory where whenever you type in nick2.stanford.edu, really that gets translated. There's a little lookup that happens that translates that into an IP address. And then the IP address is what's used from there on out for the packets, as we'll see. So how does a packet get, how does any of this work? So I need to introduce this character, the router. So a router is a bit of networking equipment that's connected to 2 or more networks, and it basically shuffles packets back and forth. So it can pick up a packet from one side and translate it over to another network. And so you can think of the internet as sort of built up collectively by all these routers. So if we were to look at my office, let's say here's my computer, 171.64.64.166. And my computer is connected, I will say, upstream to a router, 171.64.64.1. And essentially what happens is my computer gets its internet service through this router. This router sort of provides service for my computer. And as kind of a first approximation, what happens is, well, if my computer wants to send a packet out to the internet, it just sends the packet, I'll say 1 hop, over to this router, and then now it's the router's problem. The router will then in turn send the packet onto some next router, whatever, it sort of goes off onto the internet. And I'll look at a little more detail how that works. One pattern you'll notice is that a lot of times, so maybe here's my computer and a few computers' offices next to mine. A lot of times the router will have the .1 or .2 address. The rightmost number will be small, and then it's servicing all the computers with .50 and .166, whatever computers over here. All right, so let me get. So the question I'll phrase, the biggest question is like, all right, well, how does a packet get from one side of the internet to the other? And the answer is basically hop, 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 like little bunnies. So let me show you how this works. So let's say here's my computer, and let's say my computer wants to send a packet across the internet over here to about 30 miles away to codingbat.com. So what's going to happen is my computer will make up a packet, which I've drawn here with sort of the dotted outline. And without going into too much detail, I'll say this is an IP packet used for TCP/IP. And an IP packet, it has some addressing that's just standard on it. It has a from address and a to address. And these correspond to not all the computers in between, but the endpoints. So where was it originally from and where ultimately is it supposed to go to? So the way this is going to work is that my computer will make up this packet, and it'll send it one hop upstream to my computer's router, which we saw in the earlier diagram. Now this router is maybe fairly simple. It only has a few connections, and so it'll look at the packet and it just has to decide, well, which way do I send this to get it one step closer to its ultimate destination? Now for this router, it'll send it in turn upstream to its router, a slightly bigger, more expensive router. That's a second hop. And this process continues where each router looks at the packet and has to make a decision, well, which way do I send this? And it's tricky for it to know, but it is feasible. In particular, each router doesn't have to know a map of the whole internet. It just has to sort of know its neighborhood. As a practical matter, the way this kind of works basically is it's like capillaries and arteries, where down here at my office, these are just little machines and little routers, and not much going on. So the packet sort of gets forwarded up to what you would call a core router. Eventually there's some very large, very expensive router that actually knows a lot. And so on the core, it'll sort of hop over sideways until it gets to the nearest core router to the ultimate destination. And then it kind of hops down again to the sort of capillary level until eventually it gets over here to codingbat.com. Or I guess it is surprising that every time you watch a YouTube video or send an email or whatever, any that sort of data with the packets are actually making this fairly large number of hops, just hop, 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 hop from one place to another, one router to another to get where they're supposed to go eventually. So I'll just talk about routers for a second. As I mentioned before, yeah, they don't know the entire route. Each router just knows kind of locally what's going on. Also notice in that explanation, my computer doesn't really know anything about the layout of the internet. Essentially, it's delegated to the router. It says, hey, router, here's a packet. You know how to do routing. You take care of it. I should mention that routers are. It's not that all the maps of kind of which way things go are done statically. Instead, the routers are dynamic. They're always sort of measuring which links are overloaded or which ones are functioning or not functioning or whatever, and they will automatically route around breakage. So the whole system has a sort of dynamic healing quality. As I mentioned earlier, for Ethernet, routers are another example of a distributed collaborative system, that they cooperate with each other, sort of working all together to solve the routing problem for these packets. This is just sort of a detail, but I should mention there are certain special IP addresses, so 10 dot any three numbers or 192.168 dot something. Those are special local IP addresses, and they're not valid out on the internet at large. They just sort of work within an organization. And the way it works is that when a packet with a special local address like that is making its way along, hop, 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 it'll get translated to be a real IP address. The reason I mention this is that oftentimes Wi-Fi routers will give out these special local addresses. And so if you're playing around with your own equipment, you may see these. And so that's why I wanted to explain what it was. So given that level of explanation, I can talk about, well, what does it mean to be on the internet, to have a connection to the internet? And generally the way that works through Wi-Fi or through Ethernet is it means, well, you establish a connection to some upstream router, and then it's going to handle traffic for you. And actually, I'll just bring this up here. So this is the the Mac networking panel, and here I've clicked on TCP/IP, so I didn't just make that up. And I'll just point out some of the major things here. So when you connect to, let's say, a Wi-Fi router, as I have here, generally it'll give you an IP address, sort of temporarily. Say, okay, well, you can use this IP address for now. Notice this is a 171.64 address, so that's in the Stanford neighborhood, so that makes sense. So you get an IP address. You'll also tend to be able to see the IP address of the router that you've associated with. So I'm associated with 171.64.71. Also notice that, as I said, the router ends in .1, and it's maybe providing service for all these 171.64.70 IP addresses. And finally, a lot of times there's a system called DHCP, Dynamic Host Configuration Protocol. DHCP is just a way for the router to inform my computer of a bunch of other parameters about how networking works around here. So very often you'll see DHCP is set saying, oh yeah, when you talk to the router, just basically do whatever it says. So that's a you can look in your own network control panel if you wish, and hopefully you'll see a lot of this terminology actually appearing. All right. So what I want to show you, just kind of for fun, is a couple networking utilities that you can use to play around with this a little bit. This is not something you need to do yourself, but if you wish to, you could. The utilities I'm going to show you are called ping and traceroute. And on whatever kind of computer you're on, there's very likely some variant of these is available. So I'm gonna type these in the command line. So ping, if I say like ping www.google.com, what ping does is it sends a single packet out to some other computer. And what that packet basically says is, hey, are you there? And computers are not required to respond to ping packets, but if they're polite, they will, and Google does. And it just sends back a single packet basically saying yes. So if you ping another computer and you get back a response, it's really kind of telling you two things. It tells you that, well, that other computer is switched on and functioning. And it tells you that the network, all the various hops between you and that computer, those are all functioning. When the ping, so it sends it once a second, and what it does for each one is it reports how many milliseconds it took. So a millisecond is 1,000th of a second. And so this is sending wherever www.google.com is. It's sending a packet, hopping over there and hopping back, and it's taking something like 4 milliseconds each time. So let's see. So I think ping actually has sort of entered a little bit just the vocabulary of regular people, where you'd say, oh, well, is so-and-so going to the party? Oh, I'll ping them and see. It's just kind of means sort of a quick, hey, are you there sort of message. So you can use ping if your network doesn't seem to be working or whatever. You want to do sort of like a little basic checking. Ping is one way of seeing if stuff works. So a relative of ping, a more complicated utility I'm going to use here, is called traceroute. And I'll do a traceroute to codingbat.com. Where's that? Oh, I'm sorry. There. Now I'll do traceroute to codingbat.com. What traceroute does is it maps the hops between your computer and some other computer. And so it's sort of amazing. So I'm starting off here at 171.64. whatever. And so what this is saying is that was 1 hop away, that's 2 hops away, 3 hops away, and so on. And so it's kind of just mapping the path between 2 spots on the internet. So we're not going to have to get too much into the details of this, but you can see, well, I'm at, so this first hop away, that's 170, so that's some Stanford computer. That's probably some box the size of a hardback book in some closet somewhere on the floor of this building. Here's some probably slightly larger book. We're probably still on campus here. You can see at some point it jumps over to this by hop 5. We're at 137.64, something or other, scenic.net. I'm guessing that that's some provider that Stanford pays, probably a fairly large monthly bill, to be the sort of big upstream for Stanford's networking. So this is probably more of a core router. As with ping, you can see it gives you the milliseconds for that's the round trip time. So what's happened is my packet has kind of made it on a few Stanford routers over to the scenic router, and then at some point, following my artery capillary analogy, it's probably sort of making its way back down. Linode is where codingbat.com is hosted, and so now we're down on some Linode equipment, and then eventually here, that's actually codingbat.com. So as I said, that's about 30 miles from here, and so that was 11 hops. This also gives you, to me, a little bit of a sense of how fast it is, right? So that's 11 hops out, 11 hops back, and it does the entire round trip in 0.005 of a second. So you do get that feeling like, oh, right, this computer stuff, Moore's Law, it's pretty fast. So what I wanted to do, I was sort of playing around with like, well, what's something farther? So eventually I found a Poland.pl. So obviously this is in Poland. So what we'll see, so the trace route is taking a little longer here. So the first few hops are the same, right? It's still just some closet in my building, whatever. It gets out to the scenic. This is all sort of the same. But now it's routing over to level3.net, so that's just a big provider. And you see the milliseconds here are still fairly low. And then when it gets to tinet.net, 89.194, notice the milliseconds has jumped up from 2 milliseconds to 202 milliseconds. I think what you see here, I'll highlight the two lines, I think that was the Atlantic Ocean. I think when it went from this level3.net, probably then there was a big fiber optic link where it went, and now it's made its way to Europe. And the speed of light and whatever does actually enter into this. Like it does take time in milliseconds to get a signal that far. So now that it's over, I'm just guessing this is somewhere in Europe. And now it makes its way over a little bit and eventually it gets over here to Poland. And you can see, it took something like 200 milliseconds. Again, that's the round trip time, so that's pretty neat. So one thing you can see here, well, partly it just shows that the sort of hop quality. Yes, every packet, every YouTube videos, everything you've seen, all that data was making this sort of crazy large number of hops sort of getting from place to place. That really is how it works. The other thing to notice is that this is something like 8,000 miles away. So it's not that hops don't just go up linearly with distance. There are, there's fiber optic links under the oceans, whatever. There's certain links that cover a vast amount of difference, and then maybe it'll get down to a particular city and then have a lot of hops on a campus or whatever to get to the final destination. So that's not something that you don't need to run ping and trace route yourself. I just want to demonstrate those, but if you want to play with them, you can give them a shot. And I guess in the CS101 sense, like that's really how it works.